In this video, we will be looking at linear and quadratic relations. Linear relations are things that you saw in grade 9, so we will start with that to see something familiar, and then we'll move on into quadratics and see what a quadratic actually looks like graphically. So let's start with our first linear example. Bob's dog is out for a walk, and the dog's distance y in meters from the house after x seconds can be represented by the equation y equals 0.2x plus 5. We know this is linear because it is in y equals mx plus b. So the first part, we're just going to complete our table of values so that we can graph this relation. And just like in grade 9, I have set up a bunch of x values for you to sub into the equation to get your y coordinate, which represents the distance. So I've already done 2 for you. So at time 0, instead of x, I put 0. So 0.2 times 0 is 0, plus 5 is 5. So at 0 seconds, the distance is 5. So I'm going to go ahead and plot that point right there. Then at 10 seconds, I replaced x with 10. 10 times 0.2 is 2. And then 2 plus 5 is 7. So then I can plot the point 10, 7. So I'll go ahead and do that as well. Now I want you to pause the video and fill in the rest of the table on your own and then plot your points. Don't worry about that first differences column for now. So please pause and finish it off. All right, so when you did sub your values in, I'm going to do one more. So 0.2 times 20 is 4. And then when I add on the 5, I get 9. And then at 30 seconds, the distance will be 11. At 40, it will be 13. And at 50, it should be 15. So if you plotted your points, hopefully you had something like this. And then you can connect your dots with a ruler because it is linear, and we can draw an arrow at the end. So now it says to calculate the first differences. Now remember, for your first differences, you're taking all of your y coordinates, which I will highlight, 5, 7, 9, 11, 13, and 15, and you're going to subtract them. But you're going to make sure you do the bottom number minus the top number. So for this first one that I've done, 7 minus 5 is 2. I'll do another one. 9 minus 7 is 2. Now I want you to pause the video and finish off those last 3. Okay, so 11 minus 9 is 2, 13 minus 11 is 2, and 15 minus 13 is 2 as well. So now we should notice that all of our first differences are the exact same. And that is what I mentioned right here. Now, what does that mean in terms of our relationship? It means that the relationship is linear. And these are things we already knew from grade 9. So, graphically, you just have a straight line. Your equation, y equals mx plus b, is the hint that it is linear. In terms of your variable, and I'm going to focus on the x here, you only have an x term. Not x squared or x cubed, not x to the power of a negative number, it is just x. And for your table of values, your first differences are constant or equal. So that is all review, hopefully. So now let's move on and look at what a quadratic equation and graph might look like. So a swimmer dives into a pool and then submerges. The swimmer's height above the water, y in meters, after x seconds can be modeled by y equals 0.1x squared minus 1.2x plus 1.1. So just like before, the y is going to be your height here, and x will be the time. And again, I've created a table of values here. I've set your x values for the time, and you're going to have to calculate the y, which is your distance. So I've done the first 3 for you. So the difference between the linear and the quadratic is that we have x in 2 different spots right here. So when I'm subbing in my value, I have to do it 2 times. So when I set x equal to 0, I did 0.1 times 0 squared minus 1.2 times 0 plus 1.1, because there was that x in two different places. And if you plug this into your calculator, or if you just use BEDMAS, you will get 1.1. Now, for number 2, I just want to go over the BEDMAS idea in case you are going to do that, and just to refresh on BEDMAS. So I replaced x with 2 here. Now, when you're doing BEDMAS, make sure you do your exponents first. So right over here, I'm not going to do 0.1 times 2 and then square. I'm going to do 2 squared first. So I'd write 0.1 times 2 squared is 4 minus 1.2 times 2 plus 1.1. Then I do my multiplication and then add or subtract everything together to get that negative 0.9. So I want you to pause the video here and again, ignore the first and second differences and just try the substitution part. Take your x values that I've laid out for you, so 6, 8, 10, and 12, and sub them into your equation and then simplify it using BEDMAS and your calculator. All right, so for 6 seconds, hopefully you got negative 2.5 meters, and for 8, negative 2.1, and then negative 0.9 for 10, and 1.1 for 12. Okay, now if something went wrong, if you didn't get that, check to see if you followed BEDMAS. And the most common mistake here is that people forget to do the exponents first. All right, so now that we've completed our table of values, let's go ahead and take this data and graph it. So at 0 seconds, we had a height of 1.1. So we're just going to estimate it roughly here. 4 squares is 1 meter. So 1.1 might be somewhere kind of there. And then at 2 seconds, we were at negative 0.9. So maybe somewhere here. At 4 seconds, we were at negative 2.1. At 6 seconds, we were at negative 2.5. And then at negative 2.1. And then at negative 0.9. And then at 12 seconds, we're at 1.1. Now this point at 1.1, it doesn't actually make sense because you're not going to fly back up out of the water. So I have it there to help me draw my curve, but it doesn't actually make sense in terms of the parabola and the word problem. So now I'm just going to connect my points here, and there we are. And I am going to go back here, and I'm going to erase this part that came up above the water, because once you break the surface, you're kind of going to stay at that height of 0 on the water surface. So let's look at question C here. What do you notice about the graph and its shape? Well, you might say that it has this U shape, which we actually call a parabola. Now we want to calculate the first differences, and something that we already know about the first differences is that if the first differences are the same, it is a linear relation, and we can clearly see that it is not linear. So let's see what happens with our first differences. So here I have done negative 0.9 minus 1.1, and I got negative 2. Then I did negative 2.1 minus negative 0.9, and be careful with this double negative here, it actually becomes addition, and you get negative 1.2. And then if we continue, negative 2.5 minus negative 2.1, and that double negative again becomes addition. So I'm doing negative 2.5 plus 2.1, and I get negative 0.4. So I want you to pause the video here and complete the rest of your first differences by pairing up the y values. All right, so for the next one, we should have negative 2.1 minus negative 2.5. Make sure you're doing bottom minus top, and you get positive 0.4 because of that double negative. And then negative 0.9 minus negative 2.1 is going to be 1.2. And then 1.1 minus negative 0.9 will be positive 2. So if we look at these first differences, they are all completely different. They're not constant, which tells us that it is not linear. Okay, so let's make that conclusion. The first differences are unequal. This means the relation is non-linear or not linear. So let's see what happens when we calculate our second differences. So I've done the first one for you. Negative 1.2 minus negative 2. So notice I just took these first differences and now I'm going to subtract these pairs of values. And when I do that, I get 0.8. I'm going to do the next one. Negative 0.4 minus negative 1.2. That double negative means addition. So I'm really doing negative 0.4 plus 1.2. So I get 0.8 again. So I want you to finish those last 3 rows and see what you get. So hopefully you got 0.8 for all of them. So our second differences are all the same when it's a quadratic. So if the second differences are equal, this means the relation is quadratic. And if it is quadratic, it has this parabolic shape. Okay? So we can see the shape is that U shape, that's called a parabola. We see that the second differences are constant, and if you look at the equation, we no longer just have an x, we have an x squared involved as well. Now, let's take this swimmer scenario, and we're gonna add some terminology here. So, first question, what is the initial height of the swimmer? So if I go to my graph here, my initial height is where the diver started, and they started at a height of 1.1. And we know that from the table of values as well. So 1.1 meters. And this point is called your y-intercept. And this is a point that we already know. We already know what a y-intercept is. We've seen it in linear relations as well. Let's go to the next part. What is the minimum height of the swimmer? Okay, so if I go to my graph here, the lowest point is right over here. And the minimum height looks like it's at negative 2.5. And again, you can check with your table of values. Then it says, when does the minimum height occur? So if I look over here, my minimum height occurs at 6 seconds. Now this point that we just kind of referenced is called the vertex. So it is this point right here, 6, negative 2.5. So the vertex is the tip of that parabola. Let's move on. Draw a dotted vertical line through the vertex of the parabola. This is called the axis of symmetry. What is its equation? So I kind of already drew that vertical line here. And this line just cuts your parabola in half, and it's symmetrical on each side. And because it's a vertical line, the equation is x equals something. And that x value is 6. So that is your axis of symmetry. X equals 6. Now, would you say that this parabola opens up or down? So if we look at it, we see that the opening is at the top, so it's opening up. And finally, when does the swimmer hit the water surface? Well, if we look at it, it's actually in 2 different points. They hit the water surface when they're going into the water, and it looks like it's about 1 second roughly. And they hit the water surface again when they get out of the water. So it looks like at 1 and 11 seconds. And these values are on the x-axis, so these are called our x-intercepts. Now, x-intercepts have multiple names. They can also be called our zeros. So let's write those in. At 1 and 11 seconds. Okay, so let's take this word problem and kind of summarize it for the general properties of a quadratic relation. So First thing, the standard equation of a quadratic relation is y equals ax squared plus bx plus c. And I'm going to highlight this x squared term. That's what makes it quadratic, because we don't just have an x anymore. Now, which differences are constant for us? It is the second differences that are constant. The first differences are only constant if it is linear. Parabolas can open up or down. Now, we saw one that opens down, but I'm going to show you one that opens up right now. The y-intercept of a parabola is where the parabola passes through the y-axis, and the zero of a parabola is where the parabola passes through the x-axis. Zeros can also be called x-intercepts, but they can also be called roots. We don't use that one as much, but all three names mean the same thing. Now, I'm going to draw the most basic parabola we have, and that most basic parabola is y equals x squared. So we're going to create this table of value for that equation. So I'm going to take all of these x values here from -4 to 4, and I'm going to plug them into this equation, which just means I'm going to take each x value and raise it to the power of 2. So I'm going to take this -4 and raise it to the power of 2, and a negative number squared is going to be positive, so that's 16. -3 all squared means -3 times -3, which is 9. -2 all squared is 4. -1 all squared is 1. 0 squared, 0. 1 squared, 1. 2 squared, 4. 3 squared, 9. 4 squared, 16. And now I'm going to plot these points. So -4, 16. -3, 9. -2, 4. -1, 1. 0, 0. And then the same thing on the other side because of the symmetry. And then I will connect these dots as best as I can to create this parabola shape. And notice that this parabola opens up. Now I want to continue with our key properties, but ones that we haven't seen before, because the y-intercept and the zeros, they are things that we know. We know what intercepts are on the x and the y-axis. But what's new to us is the vertex. And the vertex of a parabola is the highest or lowest point, or it's the tip of the parabola. So it is that maximum or minimum value, the highest or lowest. Now the optimal value is the value of the max or min, and it represents the y coordinate of the vertex. The axis of symmetry is the vertical line that cuts the parabola in half. And it is the x coordinate of the vertex. So I'm just going to go to our parabola here, and my vertex is right here at 0, 0. And that's actually also our x-intercept and our y-intercept. Now, the minimum is that 0 value, and this is my axis of symmetry. And the equation of my axis of symmetry is x equals 0, because it passes through 0 on the x-axis. Now, the final property is something a little newer. It is called a step pattern, and the step pattern starts from the vertex. So I'm going to go from my vertex, and I'm always going to move to the right or left 1 unit, and then I'm going to see how much am I moving up to get to my next key point. So when I move to the right 1, I move up 1. Then I move to the right 1, and I move up 3. Then I move to the right 1, and I move up 5 to get to this next key point at 9. Then I move to the right 1, and I'm moving up 1, 2, 3, 4, 5, 6, 7. And that's going to be the exact same thing on the left as well. So I'm going to do it one more time. To the left 1, up 1. To the left 1, up 1, 2, 3. To the left 1, up 1, 2, 3, 4, 5. And to the left 1, up 7. So this 1, 3, 5, 7, it's all the odd numbers, and that is your step pattern. And for now, it might not mean much to us, but it will be important when we start graphing. So it is good to keep that in mind. So just to go over those key features, we have the y-intercept, that is important, the zeros, the vertex, the optimal value, which is the highest or lowest, and the axis of symmetry, and then the step pattern. Now let's just practice identifying these on two more parabolas. So looking at this first one on the left, let's start with the y-intercept. Here's my y-intercept right there because this is my y-axis. So my y-intercept has the coordinates 0, -3. Next, let's do the x-intercepts, or the zeros. The zeros are on the x-axis, so that there's one at 1 and one at -3. So I'm going to write them as coordinates. -3, 0, and 1, 0. Make sure you write them as two separate things. Okay, let's look at the vertex. My vertex is right here. And it is at -1, -4. And what this means is that my vertex is a minimum because it's the lowest point possible on my parabola, and the minimum value is -4. And the vertex is also the point where my parabola is split in half, so that my axis of symmetry, which I'm just going to shorten as AOS, has the equation x equals -1. And I can see here that my parabola opens up, and there we are. That's perfect. Okay, let's try one more example here. Here my parabola opens down. Let's start with the y-intercept again, which is right over here. And the y-intercept has the coordinate 0, 12. Then something also a little familiar, we have our zeros right here and here. And we have one at 6, 0, and the other at -2, 0. And finally, the newest point would be our vertex. It is the tip, and the coordinate is 2, 16. Now, because my parabola opens down, that means I have a maximum of 16. And here's where my parabola is cut in half at the axis of symmetry, and its equation is x equals 2. So there's a lot of new terminology here, so you do have to practice it, because practice does make perfect. So once again, we have the y-intercept, the zeros, and the vertex. And the vertex results in two key features: your axis of symmetry, which is the x-coordinate, and your optimal value, which is the y-coordinate.